So yesterday we talked about what these polynomial functions are, how to identify them, and what they look like. Now, after spending a few examples graphing them, I hope you notice that every single polynomial function you graph, the domain and range were all real numbers, right? Basically, the graphs were nice and smooth. There were no holes. They went forever to the left and to the right. So in a sense, most polynomial functions, they will take on every single value you can think of. They're basically substitutes for numbers. How polynomial functions behave is similar to how regular numbers behave. So it sort of makes sense that we can do arithmetic with them. And that's why you see today's lesson goal is to be able to add, subtract, and eventually multiply polynomials. And it's using concepts that we hopefully have already learned in the past. We don't have to reinvent the wheel. So let's go ahead and talk about it. Let's talk about adding and subtracting polynomials. Looks a bit zoomed in, but there we go. The idea is pretty simple. All it is combining like terms. Right? It isn't a complicated idea. It isn't a difficult idea. It's just basically putting all the like pieces together. For example, suppose I asked you to add, I don't know, 4x squared minus 6x minus 6, and I want you to add 8x squared minus 7x plus 4. Now, I added the parentheses for emphasis just to denote that this polynomial is different than this polynomial. But remember, in math, there's only basically two things that can keep parentheses up. Exponents outside parentheses and multiplication in front of parentheses. Well, neither parentheses has an exponent other than 1 outside of here, and there aren't any coefficients. There's nothing multiplying the parentheses. So in this particular instance, the parentheses, they're sort of redundant. We do not need them. So if you're adding and there's nothing multiplying, there's nothing outside the parentheses, you can actually drop it. Now the name of the game is simply combine like terms, right? We can group all the x squares together, we can group all the regular x's together, and then we can group all the constants together. That's it. You're done. Easy peasy. So just combine like terms. So let's work on the yellow, the x squares. 4 with the plus 8 is a positive 12. Let's work with the x's, the reds. Negative 6 with the negative 7 is a negative 13. And let's work with the constants, the pink. Negative 6 with the plus 4 is a negative 2. Boom, we added those two polynomials together. I do have an advice or suggestion for you, though. When it comes to subtracting, I hate to admit it, but you guys sometimes make mistakes. So if we take a look at this example, 8x plus 6 minus 5x squares, and I want to add to it, subtract from it 2x cubes minus 3x squares plus 7, my suggestion is this. Again, I can only break down the parentheses if there's nothing in front or if there's no exponents. But technically speaking, we do have a negative 1 in front of this parenthesis, so it would be wrong of me to just eliminate the parentheses. So I would suggest you do every single subtraction problem. Go ahead and distribute that negative in. So then this will give us 8x plus 6 minus 5x squares, and then distributing the negative, minus 2x cubes plus a 3x squares, and the minus 7. Now you can go ahead and combine like terms. So I don't get confused. I always have a technique. I always start with the biggest exponent. So if you look at the entire problem and just look at the exponents, I hope you guys can see that the biggest exponent is a 3. But notice, you only have one term that has an x cubed. So guess what? He's all by himself. Negative 2x cubes. Then move down from an x cubed to an x squares. Highlight all the x squares. So here we go. And then combine them. negative 5x squares with a positive 3 is a negative 2x squares. Then move on to the regular x's. I get an 8x here, and guess what? He's by himself. So there we go, plus 8x's. And then lastly, the constants. I got a plus 6 here and a minus 7. A plus 6 with a minus 7 is a minus 1. There we go. We subtracted. Okay. So you don't have to do this, but I highly, highly, highly recommend it if we're prone to making mistakes. Every single time we subtract, go ahead, get some insurance, and distribute the negative. Adding, subtracting, combining like terms, easy concept, I hope. When it comes to multiplying polynomials, the idea is simply distribution, as we did before, but specifically repeated distribution. Right? I know some of you guys like to use the term FOIL, and that's okay if you're multiplying two binomials, but what if you're not multiplying two binomials? What if you're multiplying, I don't know, a trinomial, 3x squares minus x plus 4, and you're multiplying by x plus 2, right? So FOIL would not work here because we don't have the right number of terms. Instead, I like to think of repeated distribution. Take all the terms from one polynomial and distribute it to every single term in the other. I do have some hints though, but take it or leave it. You don't have to do this. You're going to get the same answer either way, but it sort of makes it easy for me. I distribute from the polynomial with the fewest number, I can't write, fewest number of terms. I don't know. In my mind, I guess it just makes the process a little bit easier. I mean, it sort of doesn't really matter. What I mean is, in a distribution problem, you can distribute to the right, or you can distribute to the left. It really doesn't matter which direction you go. I like to distribute from the fewest number to the greatest number. That's what I'll show in my notes. But if you just like going to the right all the time, do it. So let's go ahead and distribute. So I'm gonna, since x plus 2 has the fewest number of terms, I'm gonna start here. So start with the x's here. So I'm gonna distribute the x to every single term. X times 3x squared is a 3x cubed. X times a minus x is a minus x squared. X times a plus 4 is a plus 4x. Notice I've done every single term in the first polynomial, so I'm done with the x. Now it's time to distribute the plus 2. 2 times a 3x is a plus 6x squares. 2 times a minus x is a minus 2x. And then a 2 times a plus 4 is a plus 8. Once you do the repeated distribution, it's just like adding, subtracting. Go ahead and combine like terms. I hope we notice that this guy here is by himself, so I'll just go ahead and copy him down. Then I'll move on to the squares. I have negative x squared here and a plus 6x squared there. So that's going to be a plus 5x. I have a plus 4x squared, excuse me. I have a plus 4x with a minus 2x, so that's going to be a plus 2x. And of course, we have this lonely 8 by himself. So you have a plus 8. Okay, there you go. So that's basically it. There's no secret, there's no trick to operations with polynomial functions. I do want to, I guess I'll call this a note. I do want to make a mention that multiplying is a binomial operator. That is to say, you can only multiply two things at once. Meaning, if I had an example that had to multiply more than one piece, or more than two pieces, say x minus 3, x plus 7 times x plus 1, you just go ahead and take it two at a time. You can't sort of like, I'm going to distribute this to everything. That would be a false move. You can't do that. So you have to make a decision. Pick two to work with. It really doesn't matter which order you multiply because multiplication is commutative. I sort of like to save the first guy as my last step. So for the first part, I'm just going to go ahead and multiply these two guys together. Again, it's just purely my choice. There's nothing that says, oh, that's the easy choice. It's purely my personal preference. What do I do with the guy that I'm not highlighting? Just copy them down. Anything you don't work on in a problem in your subsequent steps, just copy them down. So let's go ahead and multiply out the highlighted part. So we got x squares. Let me put in parentheses here. X squares plus x plus 7x plus 7, and then I'll go ahead and combine like terms. Notice I just copied the x minus 3 because I'm not doing anything to him yet. And combining like terms, we got like terms in the middle here. We have x squares plus 8x plus 7. Right. Now that I've completely finished the highlighted portion, I can then go ahead and do the distribution with the x minus 3. So it becomes an exercise of the previous example. So I'll go ahead and go through this a little bit faster than the one before. So let's go ahead and distribute this x here. X times x squared is x cubed. X times a plus 8 is a plus 8x squared. X times a 7 is a plus 7x. I'm finished with all the terms here, so let's go ahead and distribute the minus 3. Minus 3 times x squared is a minus 3x squared. Minus 3 times an 8 is a minus 24. X, and a minus 3 times a plus 7 is a minus 21. And now, of course, it's time to combine like terms. The x cubed is by himself, so I'll just write him down. In terms of the squares, I have an 8 with a minus 3. So 8 with a minus 3 is a positive 5. And they were x squares. Let's move on to the x's. I have a plus 7 with a minus 24. So a plus 7 with the minus 24 is a minus, what's that? Is that a 17? Yeah, minus 17x. And then, of course, I have this lonely minus 21 that he has nothing to combine with. So you just copy him down. Right? So that's sort of the idea. If you're ever multiplying more than two things at once, just take it two at a time. Now, repeated distribution will take care of every single multiplication problem you'll come across. But you know what? We always like patterns. We like shortcuts. And if you have the attentive eye, there are some special patterns that will save you a lot of headache. Now, let's just say, on the day of the quiz or the test, you completely forgot these special patterns. Is it the end of the world? No, it just means you have to do the long way. But hopefully you can spot these special patterns to make life simple on yourself. Right? So what are some special multiplication patterns? Well, you have the product of conjugates. And we've already done this pattern. The products of conjugates says this. What happens when you multiply two conjugates? Notice it's the same binomial, but one's a minus, one's a plus. You don't have to do all the fancy foiling, right? Every single time you multiply two conjugates, it's always the first guy squared, always a minus, the second guy squared. When you multiply two conjugates, the middle terms would always cancel out. So for example, right? It could even look something like crazy complicated looking. I don't know, 7x minus 3 times 7x plus 3. Right? I could do the FOIL. There's nothing wrong with it. But I notice, you know what? These guys are conjugates of each other. So I don't have to do any fancy foiling. I know it's going to be the first guy squared. So it's going to be 7x squared minus, and it's always going to be minus the second guy squared. It's going to be minus 3 squared, right? And this should be a little bit easier to do. Oh yeah, that's easy. That's 49x squared minus 9. Boom. I got the product without foiling. So this would be a good pattern to know. Another good pattern to know are squares of binomials. What happens if you have a binomial, say a plus b, and you square them? Well, normally that would mean, and I'll do this on the side, but you won't have to write them down. Normally that would mean, oh, gee whiz, squaring. I got to write it down twice and do the good old-fashioned FOIL, right? And you could do that, totally. That will always work. Take some time, but it will always work. Instead, this guy always follows a particular pattern. It goes, it's always going to be the first guy squared plus 2 times both of those pieces multiplied together plus the last guy squared. And the only thing that changes, if instead of it was a plus, but it was a minus problem, is this symbol here. So if you were squaring a subtraction problem, it's still the first guy squared, but instead of plus, it's a minus 2 times both of them together, and then the last guy is the same, plus b squared. For example, if I was squaring something like, oh, I don't know, I'll make it even super duper crazy hard, right? 4x cubed plus 6 squared. Oh no, this is crazy complicated. You just have to remember, oh, I'm squaring a binomial. So this is my A and this is my B. That's all you have to remember. And then you just have to fill in the pattern. Oh, it's A, oh, that's not a highlight. It's A squared plus 2 times A, B plus B squared, right? All I'm doing is I'm following the pattern, knowing the first guy is A, the yellow, and then the second guy is B, the pink. So just plug it in. 4x, 4x6, and 6. And then you just have to do math. 4x squared is 16x squared. If you were to multiply this guy all out, 2 times 4x times 6 is a 48x. And then 6 squared is 36. Look how easy that was, right? I didn't have to FOIL. I didn't have to write it out twice. It just makes life easy. Well, if there's a special pattern for squares, is there a special pattern for cubes? And indeed there is. So what if you cube cubes of a binomial? Let me organize the notes a little bit better. Let me, let's see here. Let me slash this guy off. Let me slash this guy off. There we go. Cubes of a binomial. And the pattern is, okay, what if you have a binomial, something plus something, and you cube it? Normally, that would mean you have to write it out 3 times and do a lot of distribute. It's a headache. Well, the shortcut pattern is, again, I'm going to call A the first guy, and I'm going to call B the second guy, right? So it's going to be the first guy cubed plus 3 times the first guy squared times the last guy plus 3 times the first guy, the second guy squared, plus b cubed. How does it change if it's a minus instead of a plus? Well, all the positives and negatives flip-flop. So it's going to be the same pattern. Actually, I'm just going to write it down. Same pattern, right? Nothing crazy. Same pattern. So you really only need to memorize one pattern. But the pluses and minuses flip-flop. So the a cube is positive. So next will be a negative. Next will be a positive. Next will be a negative. And it doesn't matter what crazy thing I put in the parentheses. As long as you recognize the pattern, all it is plugging stuff in. So for example, if I had like, let's do 2 variables. Ooh, that's hard. xy minus 4 cubed. Well, you just have to remember, this is your A, this is your B. Oops. This is your B. There you go. So I'm just following the pattern. I'm just following the minusing pattern here. So it's going to be the first guy cubed minus 3 times the first guy squared times the second guy plus 3 times the first guy, second guy squared, minus the second guy cubed. Now it looks pretty tedious because I'm trying to make it obvious with the color coding. Trust me, once you get in the hang of this and it becomes automatic, it's pretty fast. It only seems like a lot of work because again, color coding is not fun. But all you have to do is just plug stuff in, right? All the A parts, all the yellows are X, Y. And all the B parts, the pink, is 4. So there's a 4, there's a 4, there's a 4. And then all you got to do is math, right? So xy cubed, properties of exponents, you distribute. That's x cubed, y cubed. Minus properties of exponents, you distribute the squared here. And then 3 times 4 is a 12. Plus, and then 4 squared here is 16. 16 times 3 is a 48. Minus, and then 4 cubed is 64. I mean, I did those numbers pretty fast, but hey, you have a calculator if you need it. Right. So I really like these special factoring, multiplying patterns because it saves a lot of time. Again, at the end of the day, oh no, I forgot the pattern. What is it? You could do it the long way. You could have done, xy minus 4 cubed is xy minus 4 times xy minus 4 times xy minus 4. It'll take a long time, but you'll get the same answer. My suggestion, let's memorize the pattern. So that's it. That is 5.3. Good luck.